Hi, my name is Andy Philbin. I'm a flight instructor at the University of North Dakota. I've given a number of hours of flight training in a variety of complex aircraft. This video is meant to simplify your transition into complex aircraft through focusing on the Piper Arrow and its specific system components and functions. Remember, this video is meant solely as a supplement to your training. It is not meant to replace actual ground or flight instruction. As you watch the video, follow along using the Pilot's Operating Handbook for the Piper Arrow and the applicable systems diagrams located in Section 7 of the Pilot's Operating Handbook. Remember that a good working knowledge of systems leads the pilot in command to a successful outcome of both normal and abnormal operating procedures. During an aero pre-flight, be sure to give an adequate enough inspection in order to properly identify all equipment discrepancies. Be sure that the minimum equipment list and other documents required for airworthiness are located on board the aircraft prior to departure. Be sure that all fuel and oil servicing is completed prior to departure as well. During the pre-flight, be sure to use your checklist in order to give a detailed enough inspection of each item listed on the checklist. The first item on our interior pre-flight inspection is to check the baggage area. We'll open up the baggage door and check that everything is properly secured. You notice that there's cargo tie downs that can be used to secure your survival kit. Also, you want to make sure that the tow bar is properly installed. You want to make sure that the latch is secured around the tow bar. Next, you want to make sure that the documents are located in the aircraft that are required under 91.9. The registration certificate as well as the airworthiness certificate are located behind the aft bulkhead of the aircraft. The airworthiness certificate must be apparent in the aircraft. Make sure that you find the proper aircraft registration number. UND is now placing other required documents for flight inside of these little bags. I'd like to open up the bag and make sure that you find that the registration number of the aircraft corresponds with the aircraft you're flying. Check the front page of the Pilot's Operating Handbook. Make sure that you see the proper registration number on there. Also, open the book up to Section 6 and check that the weight and balance data corresponds with what you've computed using AIMS, if you use AIMS to do your weight and balance information. Also inside of this bag is the minimum equipment list. As you open up the minimum equipment list, you need to make sure that you find the letter of authorization right away inside of the minimum equipment list. Also, you'll find that in the back, the supplements for the operation of the GPS units are located inside of this book as well. The next item on the checklist is to check the Hobbs meter and tachometer. You want to get the dispatch book and check what you see on the tach and Hobbs versus what the dispatch book actually says. As I open the dispatch book, check the MEL placards or deferment placards in certain aircraft to make sure that you see appropriate MEL'd items on here. If you do have something MEL'd, you want to actually grab the minimum equipment list binder and check that it was properly done. Next, we have the maintenance sheet, which will tell us when inspections are due on the aircraft. You want to make sure that you fall before the date that's listed on the do not overfly date. As well, check the tachometer versus what the maintenance hob says. So our aircraft today says 2,923.8 and we're at 2,903.2, so we're fine for that. Also, check the due tachometer times on the other inspections on the sheet to make sure that you're not falling outside of those times. And also check the date of last completion in correspondence with what's required under Part 91 of the Federal Aviation Regulations. Next, open the book up and check the last slip. You want to make sure that the closeout on the billing Hobbs is the same as what you see on your billing Hobbs. So I have 3724.0, 3724.0. Looks fine to me. Also in the discrepancy pages, you want to make sure that all open discrepancies have been closed out. Check the bottom to see that the corrective actions show that the discrepancy has been closed out and it's signed by a maintenance official. Other things that are commonly forgotten in the dispatch book are to check that the FCC certificate is in place if you're going on an international flight. You'll find it in the very back of the dispatch book. Also, if you're going on an IFR flight, remember that the VOR must be inspected within the previous 30 days. Looks like this one was done on 10/12 and has just a little over a week left. Next on the checklist is to release the control wheel and check that the flight controls are free and correct. As you move the control wheel to the left, make sure the left aileron moves up and the right aileron moves down. Check the opposite control, right aileron up, left aileron down. Pull the control wheel back. Stabilator goes up, stabilator back down. Okay, after that, we're going to check the static and pitot drains. Reach your hand down next to your seat, give them a push, check for any water. These link right to the pitot-static mast. There's lines that feed up from the pitot-static mast up towards the pitot-static instruments, and you can find if any moisture has gathered in this system through these vents. Next thing is to cycle the fuel selector. We know that this engine ran on the right tank since it's on the right tank position. Want to move it to the left side, then you move the position towards the off selection as well, and then back over towards right again, just to make sure that it has full freedom of motion. So check that fuel selector. Next thing we want to check on this is the alternate static source. The alternate static source on most Piper aircraft is located right underneath the panel on the pilot's side. If the alternate static source is parallel with the panel, it's in the normal position. You want to make sure that it's in that position. If it's armed, it will be perpendicular to the panel. So our alternate static source is in the normal position. Next, we move up towards the magneto switch, make sure the key's removed and it's in the off position. After which, we'll move up towards the clock. Check that the second hand is sweeping and the local time is set. You can push in the small knob and twist it to change the time on the clock if it's so necessary. The next thing is to check the flight and nav instruments. Under 91.9, they list required markings and placards for flight. Markings include the numbers on the airspeed indicator, HSI, altimeter, vertical speed indicator. If these things aren't visible, then this aircraft isn't legal to fly. Make sure you don't see any cracked glass. Check your attitude indicator. Make sure it didn't tumble or flip over. Also, check the condition of all the markings on these instruments. The next item on our pre-flight inspection is to check the compass. You like to run your hand along the compass to make sure that there's no denatured kerosene leaking out of the compass. The reason they put that fluid in there is the fact that it won't freeze, and also you like to check to make sure that the compass card is present. Again, this would be required as a marking under 91.9 on your aircraft. Next, we have the emergency locator transmitter. We check over and make sure that the switch is in the armed position. After the ELT, we'll move down to check that the heater and defroster are in the off position. The circuit breakers are in. Notice on the Aero there's only a couple circuit breakers on most models that you can pop. The landing gear and the battery feeder breaker are the only two that can really be physically popped on most Piper Aeros. Afterwards, we check that our alternate air source is closed. The mixture is in the idle cutoff position. Propeller controls full forward. The throttle is closed. After which, we want to cycle the flaps. Make sure that the flaps will easily move through all of the positions. Afterwards, I like to leave the flaps in the fully extended position in order to continue with my exterior pre-flight. We move down to the emergency gear extension lever, make sure it's in the up position. If it's in the down position, your gear will never be able to retract. After checking the emergency gear lever, we move over to the fire extinguisher. We want to make sure that the extinguisher is properly secured. So check that it's latched. Also, when you're looking at the fire extinguisher, you want to make sure that the pin is in place and you feel that there's some mass to the thing so that it's not been discharged. These dual halon fire extinguishers, after being discharged, will discharge their entire charge. 8 to 10 seconds, it'll all be gone. So if you pop this thing, it will have nothing left. So you want to check that every once in a while. After checking the fire extinguisher, we make sure that the gear handle is in the down position. The day-night switch as required. Make sure you're in the day position for day flight, otherwise your enunciators won't show up properly. Electrical switches, we make sure all are off. After the electrical switches, we're going to flick on the battery master and check that we get 3 green lights that show up. If your nav lights are on, you'll notice that they'll be completely dim in the daytime. Next thing we check is the enunciator lights come illuminated. Vacuum, alternator, and oil enunciators should be located above. After checking the enunciator lights, we make sure that we have the switch and panel lights positioned as appropriate. Since I'd be going on a day flight, I want to make sure that my switch and panel lights are off. Check the fuel gauges to make sure that you have adequate fuel quantity. Remember that the arrows at UND Aerospace aren't topped off between all flights. You'll find that they'll be filled to tabs. You'll have 50 gallons or 25 aside. Check the engine instruments prior to your flight too. If you notice, all of our engine instruments have a little white dot next to them. The little white dot is where the needle should fall during the off position. With the battery master off, all of the instruments will fall towards that position. Make sure with the battery master on that all of the needles fall off of the small white dot. Next, we want to turn on all of our aircraft lights and make a run around the aircraft to check that all lights properly illuminate. Also, you want to turn on the pitot heat. The pitot heat can be on for a total of 3 minutes on the ground. You want to make sure that the pitot mast is properly heated prior to any flight. The stall warning vane is also checked at this time, and afterwards, we turn all of our electrical switches off. To begin with the exterior pre-flight, we're looking over the windows and fuselage on the Piper Arrow. First thing you'd want to make sure is that all of our windows do not have any extremely large scratches, and that the aircraft looks like it wasn't hit by a fuel truck. The next item on the checklist is to check the flap. We'll notice that the flap on the Piper Arrow only locks into position while fully up. You'll notice that it tells you may not use it as a step when down, because you'd obviously fall. We have the actuating arm that's in the lower left-hand corner. We'd like to make sure that we check the actuator arm for freedom of motion. Underneath the flap, you'll notice a bonding strap. The bonding strap is used to discharge static electricity to the frame of the aircraft, similar to the static wick. The flap also has one static wick. The next item on the Piper Arrow pre-flight is to check the aileron. We want to check the aileron for freedom of motion. If you locate the hinge on the central portion of the aileron, you'll find an actuator arm similar to that on the flap. Check for freedom of motion. Also, the aileron has two static wicks and will move in a fashion more up than it does down, due to the fact that these are equipped with differential throw ailerons. The next item on our checklist is to check the wingtip condition and lights on the Piper Arrow. You'll notice on the right wingtip we do have an aviation green navigation light. On the rear is a white position light and an anti-collision light, and the recognition light with its plastic cover. The wingtip is designed out of plastic, unlike the metal skin of the aircraft. You'll notice that there is a counterweight on the aileron. The counterweight should be in place. The purpose of this counterweight is to stop flutter at high cruising speeds of the Piper Arrow in flight. The next item to be inspected on the Piper Arrow is the upper and lower wing surfaces. You want to take a thorough look on the upper and lower camber of the wing to make sure that there's been no damage done in flight. Excessive G-loading can possibly cause bending to the aircraft surfaces. The next item to be inspected is the leading edge of the aircraft. You want to take a thorough look down the leading edge to check for any dents or paint removal that may have recently occurred. Common damage can occur from line service personnel possibly running into the aircraft with a tug, or also you'd commonly find pressure washers creating dents in the wings as well after bug busting is done thoroughly here in the summertime. The next item the checklist calls for is to inspect the right stall strip. You'll notice that there are two fasteners that hold the stall strip in place. Make sure that it's securely fastened. The purpose of the stall strip is to induce a low-speed buffet over the stabilator to give indication of stall that is about to progress. The next item on our checklist is to inspect the right wing tie down. In wind conditions over 29 knots, UND Aerospace tied down all of its aircraft. Make sure that the tie down is removed before starting any engine. Next item on our checklist is to inspect the fuel vent. You want to make sure that the fuel vent is clear of any obstructions. Obstructions will prevent the airflow into the fuel vent, which will allow for a vacuum to be created and possible exhaustion of fuel to the engine. Some other common stage check questions are the stock jack point on the aircraft. This little bump that you see under the right wing is used with the jack stands on the Piper Arrow. Also, you'll notice there's an inspection plate right behind the stock jack point as well. Anything you notice underneath that's a metal plate with Phillips head fasteners is an inspection plate. These are used to check common inspection items while doing phase inspections on our aircraft. The next item to check on our aircraft is the fuel cap and fuel quantity. First, we'll remove our fuel cap. You'll notice there's a black rubber gasket that should be located around this fuel cap. Also, Piper Arrows are filled only to tabs at UND Aerospace. This leaves 50 usable gallons of fuel in our aircraft. After checking our fuel quantity, we're going to want to inspect our fuel for contaminations and to make sure that we do have the proper type of fuel. Simply insert the fuel sump into our fuel sump on our aircraft. Notice that the fuel is blue in color. Any water or contamination would float to the bottom of the cup. We'd notice that if there was 100 octane fuel mixed in with our blue 100 low lead, the fuel would turn clear in color. 100 is typically green, 80 octane fuel is red in color. After inspecting the fuel, we want to check out the right main landing gear on our Piper Arrow. The first thing we notice is that our tire is properly inflated. I also like to give the tire a good roll to check and make sure that the tread underneath is not worn as well as the tread on top that is exposed. Also, according to Section 8 of your airplane flight manual, 2 inches plus or minus 0.25 of required strut inflations is required on our main landing gear oleo strut. About 3 finger spaces will tell you that you have the 2 inches. The next item that's visible is your brake caliper. You want to make sure that red fluid is not leaking out of our caliper, as well that the 2 pucks inside of our caliper have ample meat still on our brake pads. This works similar to any brake pad system in your car. Millage 5606 is the red fluid used in this system. The next item we'd like to check would be the gear door. Make sure the gear door is properly attached to the aircraft. It actuates automatically as the landing gear is retracted. Next, we'll notice we have our down lock switch. You want to make sure that the down lock switch is making contact with the down lock hook, is not bent in any fashion as well. Another micro switch you can check for is your up limit switch. If you reach up into the wheel well, you'll find the up limit switch. You want to make sure this switch as well is not bent. This is what turns off the red gear warning on safe light after the gear has been fully retracted. Also, you'll notice we can see an actuating cylinder up inside of the wheel well as well. Again, you want to make sure that there is no red hydraulic fluid, the millage 5606, leaking from this system. After inspecting the right main landing gear, we want to check that the fresh air inlet is free from any obstructions. After inspecting the fresh air inlet, we want to check the windshield and outside air temperature probe. The windshield can easily get covered with bugs in the summertime. If you find that it's hard to see out of your windshield, give line service a call on 123.3 and they'll gladly come and clean it off. You want to make sure that your outside air temperature probe is properly attached to the aircraft and not falling off as well. After checking the windscreen and outside air temperature probe, we want to check the oil quantity of the aircraft. If it's the winter, be sure to remove the engine cover before attempting to check the oil quantity. Remove the oil dipstick, and first, make sure and check that the black rubber gasket is in place on the top of the dipstick. This prevents moisture from entering the oil system and also prevents oil from leaking out during engine operation. We'll check our oil quantity to make sure that it falls between 6 and 8 quarts of oil. The pilot's operating handbook refers to a minimum quantity of 2, but according to UND Aerospace, we cannot operate our aircraft with less than 6 quarts of oil. Looks like our airplane has about 8. Next item on our checklist is to inspect the cowling latches after taking a look at the oil quantity. Make sure that our cowling latches are secured, and next we move down to check the oil cooler inlet. This inlet right here is not the ram air intake similar to that on the Piper Warrior. It actually leads down to the oil cooler. Here's the exit point for the oil cooler. If you reach your hand inside, you can actually feel the small radiator-like device inside of the aircraft. Up on top of the cowling as well is a strong point on the cowling to prevent any dents from occurring as the door swung open. You'll notice that the point can take a good deal of force. After inspecting our oil cooler inlet and cowling latches, we want to take a look at our exhaust stack on the Arrow. Pretty much make sure that the exhaust stack is in place. If the aircraft's cool, you can give it a wiggle to make sure that it's not falling off, but be cautious of a hot aircraft. These can be quite hot. After inspecting the exhaust, we want to make sure that our nose gear is safe as well. We're looking for 2.75 inches of inflation on our nose wheel oleo strut. Again, similar to the main landing gear, these are filled with a nitrogen gas. The service point is located inside of the cowling. Also, there would be a red millage 5606 fluid that could be spilling out of this oleo strut as well. If it were damaged, you'd notice there'd be metal on metal contact and possibly a puddle of red fluid on the ground. Notice on the left-hand side of this nose wheel, we do have a shimmy dampener. The purpose of this fluid-filled shimmy dampener is to dampen any shimmying motion as you get to high speeds with the nose wheel running down the runway. Due to the fact that it is a steerable nose wheel, it's not in a fixed position. Therefore, this device is necessary. just check that it is attached firmly to the aircraft as well. Also, we have an extension assist spring that must be intact as well on the nose wheel. We can check our main landing gear doors that they're attached properly and move towards the back where our micro switches are located. Up underneath, you'll notice the up limit switch and down lock switch. You'd like to make sure that the down lock switch is making contact with the down lock hook and therefore properly working. Similar to those on the main landing gear, you do want to make sure that none of these switches are bent. Also, we would like to check the actuating cylinder for any leaking of hydraulic fluid. After inspecting the Piper Arrow nose wheel, we want to inspect the landing light on our aircraft. Notice there is a bezel located around this landing light that should be properly in place. Typically, this is a common error on this aircraft. You do want to make sure that this is fastened. Afterwards, we'd like to check the air intakes on this aircraft. The intake right below the landing light is for the environmental system. It supplies air that flows around a shroud around the exhaust to bring heated air into the cabin, also for the window defrost. After inspecting the air intakes on the aircraft, we should inspect the alternator belt. The alternator belt is this black belt that has a pulley located around the crankshaft. Check for tension on the alternator belt. Next item to be inspected is the aircraft propeller. The main point of the propeller where most damage will occur is the face of the propeller. The face refers to the portion of the propeller that actually faces the pilot that you could see while you're flying the aircraft. You want to run your hand up and down the propeller, checking for any dings or nicks that would occur due to normal damage in flight. A next item to inspect on the aircraft would be the spinner of the propeller. The spinner can easily be damaged by rocks during a run-up or while having soft field operations as well. Run your hand across the spinner of the propeller and make sure that all screws are properly fastened as well. The purpose of the spinner is to provide cooling air into the cowling. Notice the aerodynamical shape leads any airflow right into the cowling and also reduces drag. Inside of this propeller dome is a large actuating piston which causes the blades to change their pitch. Also, when inspecting the air intakes on the aircraft, you'll notice that there's a small hole located right near cylinder number 2 on the left-hand side of the cowling. This small hole allows for cooling air to enter towards the lower portions of cylinders 2 and 4. The reason that you don't notice a similar hole on the side with cylinders 1 and 3 is the fact that baffling, or these rubber strips which lead air down towards the lower portion of the cowling, will lead air to cool the lower portion of those cylinders. On the sides of cylinders 2 and 4 on the left-hand side of our cowling, internally is the main air intake, which is located on the rear of cylinder number 4. This is the reason why there really isn't a problem with induction icing on the Piper Arrow, and therefore an alternate air source is pretty much just needed if the air filter gets clogged with debris. Moving on from inspecting the front portion of the aircraft, remember again to check on the left-hand side of your cowling the cowling latches are secured. Afterwards, you'll roll underneath the cowling and inspect the oil breather. The oil breather has an orange cover around it and is a metal tube. The purpose of the oil breather is as water vapor is released in the oil, it will be thrown out through the oil breather. If the oil breather is clogged with ice or debris, after the oil reaches a temperature of 180 degrees Fahrenheit, which is noted on your oil temperature gauge by a white line, the oil will release all water vapor due to its hygroscopic nature. As this water vapor is released, pressure will build inside of the crankcase. If the breather's clogged, there is no point for it to exit, and there could possibly be a failure of the oil system. Also, there are 3 black tubes located underneath next to the oil breather. One tube is used to vent fuel from the engine-driven fuel pump if there's excessive pressure. The other is from the electric boost pump. And the third is a vent from the intake system of the aircraft. If during engine start procedures you have an overprime situation or the aircraft is improperly shut down, fuel will bleed through a fuel valve, which is commonly called a sniffler valve, outside of this tube and leak onto the ramp. Again, there is another fuel strainer located on the left-hand side of this cowling. Similar to checking the one under the main fuel tanks, you remove fuel, check for any sediment or debris inside of the fuel as well as water, checking the proper color as before. After pre-flighting the rest of the cowling, the rest of the pre-flight of the left wing is similar to that of the right wing, except for the fact that we have 2 additional items to inspect. You'll notice that we have the stall warning vane located on the left-hand side of the wing as well. You do want to check for freedom of motion of this stall warning vane. As the stagnation point shifts rearward on the wing as you get towards the critical angle of attack, airflow will be reversed and push up on the tab to initiate the stall warning to occur. When inspecting the pitot mast, you would like to check that the front ram air inlet is free of any debris or bugs as well. There's a drain hole located on the bottom portion of the pitot tube. When looking at any Piper schematic, you'll notice that the drain hole is actually only attached to the static port side of the pitot mast. The true drain for the pitot tube is located inside the cockpit on the pitot static drains located on the lower left-hand portion. After inspecting the left wing, we want to check our lower surface antenna. One of the things you're checking for is to make sure they don't have a thick coating of oil on them. You can have erratic signals if the actual antenna are covered with oil. You'll notice that with our two types of aircraft we have here, certain have Bendix GPS and certain have a Garmin GPS. There's two acronyms to remember. 384 here is equipped with a Garmin GPS, therefore we're looking for TCAM. Transponder's the front T, GPS communications, ADF, and marker beacon antenna. On Bendix equipped aircraft, we'd have TDAM, transponder, DME, automatic direction finder, then marker beacons. Similar to inspecting the right-hand side of the aircraft, you want to check the condition of the fuselage and windows. We're checking again for any dents or scratches that may be on the windows. After inspecting the windows of the aircraft, you're to check the upper surface antennas. You'll notice on this Garmin-based aircraft we have one communications antenna. Make sure it's not too bugged up or falling off. Also, we have two GPS antennas located on the upper portion right near the door. The fresh air inlet is located on the left-hand side of the fuselage of the Piper Arrow. This supplies air for the overhead vents on our aircraft. You want to make sure that there is no debris clogging the fresh air inlet. Also located right next to the fresh air inlet is one of the static ports. Problems with these static ports located on the fuselage happen due to spiraling slipstream off of the propeller. Impact air can come into the static port and give erratic readings. Another problem that can be seen is as aircraft age with fuselage-based static ports, they can easily be dented and therefore have errors occurring within the pitot static instruments as well. Next item we'd like to check is the identification plate on our Arrow. You'll notice that this has the serial number on the aircraft. You want to make sure that this is properly secured. It is a required document for flight. After inspecting the identification plate, we'll check the left stabilator of the aircraft. One thing that I like to do while pre-flighting the stabilator is give it a little tug. Make sure that it's properly secured to the aircraft. Moving aftward, you'll notice that there is one static wick on the left-hand side of our stabilator. There's another also located on the right. I like to check the stabilator for freedom of motion and also check the rear tail cone to make sure that the bolt which holds the actuating device is in place. You'll notice a nut and bolt located inside. While checking the stabilator, the anti-servo tab should also be checked as well. Check that the tab moves in the same direction as the stabilator with greater travel. The purpose of the anti-servo tab is to prevent over-controlling the aircraft and to give positive control feel. Afterwards, you'd like to check that the tail tie-down has been removed as well. This tail tie-down has a threefold purpose. One of the purposes obviously is to tie down the aircraft. Another is as a skid if you come in too tail low on a landing. The third is, while in maintenance, the aircraft will have a weight placed on the tail tie-down to stop it from tilting nose forward while on jacks. The next item to inspect on our aircraft is the rudder. You want to make sure that the rudder has a slight freedom of motion, yet still feels attached. There is one static wick located on our rudder. Up in the upper portion of the rudder of the aircraft, there is a counterweight as well. You can notice if you take your checklist and tap upwards, you'll hear it become hard surface towards the tip of the rudder located towards the front of the fuselage. This counterweight stops flutter, similar to those located on the ailerons. After inspecting our rudder, we're to inspect the right side of the stabilator. The inspection process is exactly the same as that which we used on the left-hand side. After inspecting the right side of the stabilator, you want to check the ELT antenna. The ELT antenna is this black antenna located on the upper portion of the right-hand side of the fuselage. Make sure it's securely fastened. Also, the ELT battery is located behind this small ELT door. They use plastic fasteners on this for ease of removal in case you do need to arm the ELT manually if the switch up in the cockpit is not working. Afterwards, we do have another static port, which we must inspect similar to the one on the left-hand side of the aircraft. There is an external power receptacle, similar to that on the Warrior, located on the right-hand side of the fuselage as well. We're just checking for any clearance from obstructions and that the door is closed. Afterwards, underneath the aircraft are the battery vents. We'd like to check the battery vents to make sure that they too are free from any obstructions. The final item on our exterior pre-flight inspection is to check the baggage door. We just want to make sure that it's properly closed and isn't going to open on us in flight. You'll notice that we've ended our checklist right where we began, and we've now completed the exterior pre-flight on our Piper Arrow. Remember after each flight to perform an adequate post-flight inspection using the checklist to identify possible discrepancies with the aircraft. The first item on the post-flight inspection is to verify that the magnetos are off. Be sure to turn the key to the off position and remove it. You want to make sure that the magnetos are properly grounded in order to protect anyone who moves the propeller accidentally on the ground. The next item on the Arrow post-flight inspection is to make sure that the flight controls are properly secured. Take the seatbelt and place it around the control column and attach it. This will prevent the flight controls from flapping around in the wind. The next item on our checklist is to check for oil leaks on the exterior of the aircraft. You want to take a look underneath the engine and make sure you don't see any puddling of oil. The next item on our post-flight checklist is to check the aircraft exterior. You want to check the exterior of the aircraft, making sure that there's no dents or dings in the aircraft after your flight. The next item on the Piper Arrow post-flight inspection is to check the tires and struts for proper inflation, and also to check the tires to see if there's excessive wear. You'll know if a strut's popped because there'll be red fluid leaking from the strut, that MIL H5606 that we talked about in the gear system, and also the strut will be bottomed out. There'd be no metal showing. If you want to check the tire properly, give it a roll, and you can see if there's any flat spots underneath the aircraft. Also check for excessive wear. Maintenance won't replace a tire until tread actually shows through. It'll look like cloth coming through the tire, but excessive flat spots should be written up on the discrepancy page. The final item on the post-flight checklist is to chalk the aircraft. After a flight, you should put the red chalk in the front, symbolizing that the aircraft needs fuel. Policies and procedures also say if the wind velocity is over 29 knots at the airport at the time of your post-flight, you should tie down the aircraft as well. The Piper Arrow has Airmotive RSA type fuel injection for its fuel delivery system. The Arrow has two wing fuel tanks with a total capacity of 77 gallons with a usable capacity of 72 gallons. UND Aerospace fuels the Piper Arrow to tabs, which gives 50 usable gallons of fuel. On each fuel tank there is a fuel vent. The vent has a twofold purpose. First of all, it allows air to enter the tank to replace fuel as it is consumed. If the vent were clogged, there eventually would be fuel starvation failure of the engine. This will be caused by the vacuum created within the tank and the engine-driven and electric boost pumps' inability to overcome the force of the vacuum created. The secondary purpose of the fuel vent is to vent excessive fuel out of the tank. If the aircraft is topped off on a hot day, the cold fuel in the tank will expand and then be forced out of the vents. The caps on the tanks have a gasket which must be checked during pre-flight to prevent water from entering the system. The fuel cap is also vented. A small vent will allow for air to flow into the tank if the fuel vents become clogged. Each tank has a fuel drain on the lowest point of the fuel system. The fuel used at UND Aerospace is 100 low lead. The Piper Arrow is capable of using both 100 low lead and 100. 100 low lead is blue in color, while 100 is green in color. If 100 low lead and 100 octane fuel were to be mixed, the combination of the two would cause fuel to be clear. Jet fuel is also clear. Be sure that it is 100 low lead or 100 used in your tank. Smell the fuel. 100 low lead has a distinctive smell, as does kerosene. Kerosene smells much like diesel fuel. Jet fuel is also extremely oily when you rub it between your fingers. The number referred to with 100 low lead is octane. Octane is a chemical property of fuel. The higher the number, the higher the octane content of the fuel. Also, the higher the number, the slower the burn rate. 100 low lead is used in our aircraft to slow the burn rate in our engines. If a lower octane fuel were used, we would have a chance of detonation. If you think back to your car, you use 87 to 92 octane in your vehicle. Higher octane fuels are required for cars with higher compression ratios or some sort of forced induction, such as a turbocharger. Most production vehicles on the market now have compression ratios around 9 to 1. meaning they squeeze 9 parts of air into a space made to fit 1. Any car with a higher compression ratio will require the use of a higher octane fuel. The Piper Aero has a compression ratio of 8.5 to 1. The reason we use such high octane is the poor mixing of fuel and air, leading to uneven burning of fuel in the aero. After the fuel is fed from the tank, it travels to the 3-position fuel selector. The fuel selector must be fully in the left or right position, otherwise fuel will not flow. Fuel flows from the fuel selector then into the filter and or gascolator, and the fuel filter will remove large debris from this to stop it from flowing through the injectors, which can easily be clogged. Also, you'll notice there is a fuel strainer right here where we can take a sample of the avgas to make sure that it is clear of debris. After the fuel is filtered, it flows to the electric boost pump. The electric boost pump is a vane type pump which provides fuel pressure for priming, or also to provide operating pressure in case of the failure of the engine-driven fuel pump. There's a small black rubber hose that comes off of the electric fuel pump to vent away excessive fuel pressure overboard. It can be found in the rear of the cowling near the oil breather. Afterwards, fuel moves to the engine-driven fuel pump. The engine-driven fuel pump is a diaphragm-type fuel pump. It takes the rotary motion of the moving gear off the accessory case of the engine and changes it into linear motion through the use of a cam. The cam lobe moves the diaphragm up and down, moving fuel through the system. Fuel flows from the engine-driven fuel pump to the servo regulator. The servo regulator is the device which meters the amount of fuel which flows to the fuel injectors. The first point of control inside the servo regulator is the fuel control unit, which is attached to the mixture control. This is a variable size orifice which controls the amount of fuel which makes its way from the pumps towards the engine. So here's our mixture control valve. This is where your red-handled mixture knob is actually attached. Notice that up here we do attach to a variable size orifice. As we pull back on this, it will limit the amount of fuel that will be allowed to pass through the system, similar to the mixture control that you had in the carburetor in the Piper Warrior. Right here is your inlet fuel pressure that will be fed into the system, and it will soon be fed towards the servo regulator where it's further metered. Here's our diagram of the servo regulator. As we said before, there are 2 diaphragms in here which control fuel output, and we'll see shortly how these work. Right here would be our air diaphragm. Here's our fuel diaphragm, both attached to a ball valve assembly, and we'll see how this moves in a second. We have here metered fuel pressure, and here is unmetered inlet fuel pressure. This will be a constant that won't change. Your throttle valve is right here, so as you move your black throttle inside of the aircraft, you'll be moving this butterfly valve to an open position. And here would be our outlet fuel pressure, which will flow to the flow divider. On the left-hand side of the engine of the Piper Aero is located the throttle linkage on the servo regulator. This is directly attached to the butterfly valve, which controls the amount of air flowing in through the air filter and thus in through the induction manifolds into the engine. As we move the throttle forward, we open the butterfly valve, and you'll notice the linkage moves. Moving the throttle back will close the butterfly valve, thus reducing the amount of air that flows through this system. So let's go ahead and animate this a little bit and see how this would work. So first off, we notice that we're moving our throttle right here. Secondly, we have impact air pressure. As that throttle is moved open, there'll be a higher air pressure flowing through this servo regulator assembly. So as this increase in air pressure flows through an impact tube that's located inside of the throat of the servo regulator, we'll have high pressure air flowing upwards towards the air diaphragm. The next step in this sequence is caused by this venturi shape right here. The venturi allows for a suction to be created, and that suction will draw off of the backside of this air diaphragm and cause a motion outward. Notice now, metered fuel pressure will have to increase as the throttle is moved forward, and therefore we'll have a forward pressing motion against the fuel diaphragm as well, but inlet fuel pressure did not change. That's a constant coming off of our engine-driven fuel pump. After we have both of these values pushing against this assembly, the entire assembly will now move. Our ball valve has come off of its seat, and therefore the metered fuel pressure is able to increase, which is being fed to the engine. You can see our little arrows get bigger, showing that more fuel would now be flowing to the flow divider. So the simple principle behind this, again, is just using air as one source of metering pressure and fuel as another. As the throttles move forward, increase in metered fuel pressure along with an increase of impact air and a suction created at this diaphragm, or the venturi inside of the servo regulator, will cause this entire assembly to move outward, ball valve off of its seat, increase in fuel pressure that is going to the flow divider. Okay, the idle control on this aircraft is done through the use of two adjustment screws. We have to take into respect the speed that we want the aircraft to idle at and the idle mixture control that we'd have occurring as well. Idle mixture is determined by an offset of the ball valve on this side of the servo regulator. Maintenance will adjust a screw to try to get the aircraft towards a 14.75 to 1 stoichiometric ratio of air to fuel by offsetting this ball valve at a certain rate. The offset that occurs for the speed of the engine will be up on the throttle valve. So by turning a screw, they'll be able to offset how much this butterfly valve will be open. The assembly for the air diaphragm and fuel diaphragm are not really similar to the idle speed circuit on the carburetor, the Piper Warrior, don't really come into play until higher speeds when you actually begin to move the throttle beyond the idle speed setting. Therefore, we do need this adjustment that occurs at the ball valve and the throttle valve. On the upper portion of our engine in the Piper Arrow, you'll notice the flow divider. It's the spidery looking device which distributes fuel evenly to all 4 fuel injectors. We have one line here which is a supply line off of the servo regulator. After fuel is metered by the servo regulator, it's fed to the flow divider and then down to each of the 4 injectors. A 5th line that comes off of the flow divider feeds fuel to the fuel flow gauge. This gives us our rate in gallons per hour of fuel flow right near the manifold air pressure gauge. Notice each of these 1/8 inch stainless steel lines feeds down and into one of our fuel injectors. There is a pop-head valve inside of the flow divider which allows fuel flow through the system with low power settings. The purpose of this valve is to stop air from entering the system at low throttle settings. It keeps back pressure in the fuel system. As the engine shuts down, the pop-head valve closes, keeping fuel in the line from the servo regulator to the flow divider. This stops a condition called vapor lock. Vapor lock occurs when air is trapped in the line between the flow divider and the servo regulator. Another condition which causes this is excessive heat. This is what makes the Arrow difficult to start on hot days after it's been run. After the engine is shut down, there is excessive heat in the cowling. The fuel in the line from the servo regulator to the flow divider begins to vaporize. So after fuel flows through the flow divider, it's then driven to our fuel injector. The fuel injector allows for a nice fine misting of fuel rather than a drip of fuel that would flow out of this injector. These are called CIS, or continuous injection systems, because unlike your car, the fuel flow doesn't actually ever stop. It continuously injects fuel into this engine. On the downward stroke of the cylinder, as that piston is actually moving downward, fuel will be pulled in at a stronger rate from the injector with the intake valve open. So when your intake stroke is occurring is when truly this injector will be having its pulse, or fuel flowing from the injector. The way that we prevent fuel from coming out in just random drips and causing a nice fine spray pattern is actually through this air bleed hole right here. The true name for this is an emulsion chamber. Emulsification is a process by which liquid is made into more of a vaporous mixture, and that's what occurs here. In your Warrior, in the carburetor, you'll notice that you have an emulsion tube on the diagram in the Warrior system software on your laptop. This the emulsion chamber is in a similar function, allowing a little bit of a vaporization to occur, so a fine spray pattern, which is easier to consume but for the engine, will occur from this airplane. There's also a little screen that is over this emulsion chamber which stops dust and dirt from making its way into the injector and therefore being sprayed. Think of this like a Windex bottle. The bottle has 2 settings, spray and stream. When the bottle is in the stream position, no air is mixed into the cleaner before it is sprayed. In the spray position, there's a slight amount of air mixed into the cleaner before it is sprayed, allowing it to be atomized. This is the same reaction of the emulsion chamber in the fuel injectors. The Piper Arrow landing gear system is electrically driven, hydraulically actuated, and fully reversible. The system is filled with hydraulic fluid made of Mil H5606, which is red in color. Here we have the diagram that's located in the maintenance manual for the Piper Aero gear schematic for the hydraulic side of how this system operates. You'll notice the components on the top of the diagram. Right here you'd have your fully reversible electro-hydraulic pump. So it's electrically operated, hydraulically actuated gear system is what the naming of that means. Hydraulic fluid through this pump will not flow through the gears, it flows around the gears to cause the moving force of the hydraulic fluid through this system. The components of the Piper Aero gear system for the pump and gear up and down solenoids are located in the aft, behind the rear bulkhead with the baggage compartment door removed. You'll notice that here is the gear reservoir and pump motor. There's a little placard that tells you to back off the dipstick 1.5 turns. This allows for proper venting of gases that build up as the fluid is heated through motion. Also, you'll notice here are your gear up and down solenoids, which you can find on the electrical gear schematic as well. We notice that we have 2 entry and exit points of hydraulic fluid from the reservoir up on the upper portion of this diagram. Right here we have a high pressure relief. On the upside, when we're retracting the landing gear, let's say that the pump continues to turn and high pressure is building. As you can see, we have 2,400 plus or minus 200 psi, that this will allow a relief of that fluid to flow back into the hydraulic reservoir, thus stopping a damage occurring to the system as we're retracting the landing gear and the pump not properly turning off. As a backup of that, we have a thermal relief which operates in the same fashion. If excessive pressure builds up in there, remember, anything under pressure will have an increase in temperature. At 3,000 psi, plus 300 minus 200 psi, our thermal relief will blow and allow fluid to flow into the reservoir, thus stopping damage occurring if we have a failure of the high pressure relief. Over on the low side, we notice we have a low pressure bleed. It lists a 600 psi point at which this will actuate, stopping the flow of fluid from occurring on the low pressure side of the actuating cylinders. So this will stop damage from occurring as the gear are extended outwards. Right here we see the 020 diameter bleed hole. Now what this is the point where when maintenance is servicing this hydraulic system, similar to bleeding brakes on your car, they'll remove fluid from the system until air bubbles no longer show. So this would be the point in which maintenance will bleed the system of the MIL-H 5606 red hydraulic fluid that is located inside of the system. Right here we have the shuttle valve. The shuttle valve directs fluid that's returning from the low pressure side or the extension side of our landing gear. On this side we have the gear up check valve. This diagram notes them kind of in unison to each other, but they do move independent of each other. So the gear up check valve is what will control the flow of fluid on the high pressure or retraction side. The 2 devices we see right here are fluid distributing manifolds. They're located actually under the rear seats of the aircraft, and they direct the flow of fluid towards the actuating cylinders. So it's not exactly as complicated as this diagram looks when you see it in the aircraft. We're now looking under the rear seat of the Piper Aero. We have the floorboard ripped up here so you can follow the hydraulic fluid lines for our landing gear system. Right here we have the up and down lines routing hydraulic pressure to or from the hydraulic reservoir located in the aft behind the rear bulkhead of our aircraft. Here's one of the lines that feeds fluid up towards the nose wheel. You'll notice that these 2 hydraulic lines right here feed pressure to the up or down side of the nose wheel actuating cylinder. Here are 2 lines which feed to the right main landing gear. Beneath these lines is the pressure switch. This is the switch upon reaching 1800 psi will shut off the hydraulic pump. We notice now that we do have our actuating cylinders for both the main landing gear and the nose gear. We have the downside where fluid would be forced in to cause the gear to extend, which is on the upper portion in our diagram here, and the retraction side of our cylinder. Hydraulic fluid would come into the base of the cylinder and cause these actuating cylinders to move upwards, thus bringing our gear into the aircraft. Right here we have our emergency extension valve. As this extension valve is moved forward, the pressure would be released. This is a gravity free fall system. It will allow the pressure that's on the retraction side of the cylinders to flow through these distribution manifolds back to the extension side, thus causing our gear to extend manually. Here we have a Piper Arrow main landing gear assembly. You'll notice with the Piper Arrow on jack stands, the oleo strut has much greater inflation than the normal 2 inches required on the pre-flight inspection. We'll move upwards, identifying the components on our gear schematic here. Notice that we have the main landing gear door attached directly to the gear trunnion assembly. As the gear rotates inward, the gear doors will follow. Next we have the gear down lock hook located right here. The gear down lock hook stops the gear from folding back inwards. There also on the reverse side is a trailing link as well, which will stop the gear from folding outwards. Behind is the down lock switch, which with down lock hooks engaged will have contact, and therefore the switch will be closed, allowing the green light to be illuminated for its respective landing gear. One different component on the left main landing gear of our Piper Arrow is the squat switch. With this gear on jacks, we can see that the squat switch is actually making contact right now. Therefore, power would be allowed to flow through this system with the oleo strut fully extended, allowing the gear to be able to be retracted. This is a safety precaution with the aircraft on the ground. The squat switch will be open and the gear will not be allowed to be actuated. No current can flow through the system. So as our gear pump begins to turn, we'll notice that fluid flows down against the shuttle valve. So the shuttle valve is able to move out of the way and cause the fluid to flow to the distribution manifold. As fluid flows through the distribution manifold, this would actually be occurring in all the landing gear at the same time, but for the purpose of demonstration, we'll show it occurring on one cylinder at a time. We'll notice fluid flows down and to the extension side of the actuating cylinder. We're looking at the left main right here. We're causing this actuating cylinder to move downward, fluid to fill in the reservoir here. Fluid then that was on the upside of this cylinder will be able to move through its respective distribution manifold up towards the gear up check valve. The gear up check valve will be displaced out of the way, and fluid will be allowed to return back towards the pump and also the reservoir. Now we'll notice it'll occur on the rest of the landing gear. Just as we said before, it will occur at the same time. So we notice our actuating cylinders are moving, fluid is returning back towards the pump as well as the reservoir. We can extend the landing gear in the Arrow as fast as 129 knots because we have this delivered 600 to 800 psi that's going against this system to allow those down lock hooks to click over and engage. And what occurs to shut this pump off is the down lock switches will be activated, thus shutting off the pump in this system. All right, as power is fed to the downside of our pump, the gear will begin to move downward as the handle is put into position. Notice the main landing gear are the first to extend and the nose wheel is slowly lowered. This is to prevent damage from the reduced weight on this landing gear. Don't want it to slam in place and fly past that down lock hook. So as our landing gear is being retracted, we move our gear handle towards the up position inside of our aircraft. The pump begins to turn and fluid will be allowed to flow around the pump motor towards the gear up check valve. The gear up check valve is moved out of the way and fluid will then be allowed to flow towards the distribution manifold on the upside. So now we have fluid towards the base of the actuating cylinder, which will allow it to move upward. Fluid will fill into the small reservoir, and fluid then from the downside will be forced back towards the distribution manifold and then up towards the shuttle valve. The shuttle valve will be displaced, and fluid will then be allowed to flow back towards the pump as well as the reservoir. Now we can see that fluid would be moving through the system and causing all of the actuating cylinders to move. One noteworthy item though is as the nose wheel is being retracted, the orifice that is located on the upside distribution manifold for the hydraulic fluid will be used. Remember, the nose wheel retracts quickly due to the aerodynamical forces acting against it, as well as the fact that it is lighter than both main landing gear. Therefore, it will be the first to retract. As it comes up into the wheel well, it'll cause the hydraulic fluid that was being sent towards that actuating cylinder to reverse flow. And as it reverses flow, it will head back towards the hydraulic pump. Remember, this is like comparing towards operating a small electric toy car by hand and moving the motor too quickly. You could cause damage to the pump. Therefore, this orifice is necessary, and so is following the retraction speed, the maximum of 107 knots. As Jeff moves the gear handle to the up position, power will now be able to flow to the pump motor. Notice the main landing gear retracting first, and the nose wheel actually made it up initially. The nose wheel was the first to retract due to its reduced weight. You'll notice that as the gear made their way up, the main landing gear hesitated for a second. This is due to a resurgence in hydraulic fluid, which flows aft from the nose wheel landing gear actuating cylinder back in through the distribution manifold on the upside of this system. That hydraulic fluid causes the main landing gear to hesitate for a second before they're fully retracted. So the emergency gear extension on the Piper Arrow is done through a manual extension using hydraulic fluid, displacing it back towards our downside of our cylinders. So remember, the only force that holds the landing gear up is hydraulic pressure. 1,800 pounds per square inch of hydraulic pressure will be sent on towards the upside of these actuating cylinders. After that pressure switch is shut off, the pump will no longer run unless an emergency situation does occur. If for some reason we go through our checklist and cannot get the landing gear to extend through normal means, all we have to do is displace our emergency gear extension valve. What this will cause to happen is the emergency valve will open up. It actually twists and causes a variable size orifice to open up completely, and then fluid will be allowed to flow down from the actuating cylinders. Notice all of the actuating cylinders have now moved downward. The fluid will flow towards the distribution manifold and then over towards the other, on the downside distribution manifold. Fluid will be directed towards the downside, causing the actuating cylinders to be displaced and lock in place properly. This is why we have to slow to 87 knots. As we said before, we can extend the landing gear as fast as 129 knots due to the fact that we have hydraulic pressure to help assist bringing those down lock hooks over and in place. If you're going much faster than 87 knots, the aerodynamical forces acting on those landing gear, particularly the nose, will cause them to just flop and free fall and never lock into place unless action is taken by the pilot. One thing you can do is actually get on the rudders to cause the mains to swing outwards and use the stabilator to cause the nose to swing outwards and lock in place if you do mistakenly try to extend the landing gear at a speed greater than 87 knots. One noteworthy item on this schematic is the gear down snubber orifice. This is another restricting orifice which slows the flow of fluid back towards the downside of these actuating cylinders. If you have excessive amounts of fluid flowing too rapidly towards the distribution manifold, the gear will plop down quite quickly and could possibly cause damage to the downlock hooks, and therefore they won't properly lock in place. When you look at an aircraft on jacks with the emergency gear extension valve being actuated forward, they hesitate for a second before they lock into place. This is the action of the gear down snubber orifice and is a limitation which helps to protect the aircraft from damage. Now we'll take a look at the emergency landing gear extension sequence on our Piper Arrow. As the emergency landing gear extension valve is moved forward, you'll notice that the gear do not slam down violently. Notice the nose wheel slowly was extended. The extension assist spring helped to bring it into the position that it's in. The gear down snubber orifice located on the hydraulic diagram assists in stopping the gear from slamming down too hard and overcoming the downlock hooks. We must slow the aircraft to 87 to allow gravity to cause the landing gear to drop and lock in place. As we extend our landing gear on the electrical side, we'll look at this diagram now of the Piper Arrow landing gear electrical schematic. We move our handle downwards first towards the down position. As we do this, a micro switch will be moved as well, which allows power to begin to flow towards the downside of the down solenoid on our landing gear schematic. Remember, a solenoid is just a larger switch that is being used to move, or being moved by the movement of a smaller switch. Similar to the battery master in the Piper Arrow, as you turn on the battery master, you'll notice a click sound that you hear coming from the rear of the aircraft. That clicking is the solenoid making contact and allowing power to flow from the battery to the actual main bus off of our aircraft. So as we move our switch down, the solenoid makes contact and power will flow up to the downside of our gear pump. Power will begin to flow to this pump and the wheels of the pump motor will actually begin to turn. So now hydraulic fluid will begin to flow through our system. As the gear begin to move downward, the up limit switches will no longer be contacted anymore. Now the gear have begun to move towards the down position, so therefore our gear warning unsafe light will illuminate. This occurs when the gear is in transit. This will be shut off after the gear are in the down and locked position. But now, during our 7-second extension sequence, we'll notice that the gear warning unsafe light will be illuminated. The next thing that begins to occur is our down lock switches will begin to become satisfied as our landing gear becoming fully extended. So we'll notice that our down lock switches have moved. We now have power flowing from that circuit breaker. Notice the indicator circuit breaker, power flows from, down, and towards all of the down lock switches. After we have the switches satisfied, the 3 green lights will illuminate. After the 3 green lights are illuminated, we know our gear are down and locked, and we'll lose power towards the gear warning unsafe light. The gear warning unsafe light will turn off, and power will continue to flow up towards this solenoid. Again, big switch being moved, so we'll have power stop flowing through this system, and the pump motor will turn off, and our gear are fully extended. And remember that the Aero gear system does have a gear warning unsafe horn. There are 3 situations which will cause the horn to sound. First, if the squat switch is open with the aircraft on the ground, the horn will sound and the gear warning unsafe annunciator will illuminate when the gear selector is placed in the up position. Also, the gear horn will sound with the gear in the up position and the throttle move below 14 inches of manifold pressure. Finally, the horn will sound and the annunciator will illuminate when the flaps are extended beyond the 10-degree setting with the gear up. The micro switch for the flaps is activated when the flaps are extended beyond 16 degrees. Right now we have the main landing gear and the nose wheel retracted on our Aero. And as you can see, we'll look at the operation of the micro switches for the warning system on our aircraft. As I move the throttle rearward now, you can hear the micro switch click on. That actuation of the micro switch will allow that 90 Hertz oscillating tone to occur, which alerts us to lower the landing gear. The aircraft pretty much thinks you're trying to land and wants to alert you to bring the landing gear down. You'll also notice the gear warning unsafe light will illuminate. Another function that causes this annunciation to occur is moving the flaps beyond the 10-degree position. You'll hear a small click occur as the flaps move throughout a 16-degree arc and lock into the 25-degree position. There's the click, click off, click, here's the horn. On this schematic, we notice that we'd have the Piper Aero towards the gear down position, and this would be an on ground ready for takeoff is where we're sitting with the schematic. We have power flowing through the gear indicator side, moving towards, showing that we have our 3 green lights illuminated, also stopping power from flowing down towards where our gear warning unsafe light would appear, and also stopping power from flowing towards the downside of the pump motor. So as we take off our aircraft, you remember the first thing that will occur is our squat switch will move from the ground to flight position. The squat switch on this plane is located on the left main landing gear. As the oleo strut is fully extended, it'll make contact with the squat switch, thus allowing electrical power to begin to flow through the system. Now we get our positive rate of climb out of usable runway, and we begin to retract our landing gear. So we'll grab our handle and pull it upwards, and notice we're again moving the switches towards the up position, and power will then be allowed to flow towards the solenoid. Again, a small switch moving a bigger switch, so the solenoid will be electromagnetically driven downward, and power will begin to flow towards the upside of the motor. We now have power going through the system, and hydraulic fluid is beginning to flow. So as the gear are retracted, the first thing we'll notice is the down lock switches will no longer be satisfied. Therefore, our 3 green lights will turn off, so we've lost power flowing through these 3 green. Now, our up limit switches are not yet satisfied. Therefore, we're going to see the gear warning unsafe light appear in this system. Gear warning unsafe light is illuminated. As we further continue our retraction, the up limit switches will make contact. Remember, the up limit switches are not what turn the pump off. The up limit switches simply turn off the gear warning unsafe indication that we see in our aircraft. As we continue, the pressure will now begin to build in this system, and we're moving towards 1800 psi. As we achieve 1800 psi, the pressure switch will be fully contacted, and power will stop flowing through the system, and therefore we will no longer have power coming towards the upside of our gear actuating cylinder, and then the pump motor will stop running. The Piper Aero has either a Macaulay or Hartzell constant speed propeller. A constant speed propeller is an extremely efficient propeller design due to the fact that it can change pitch to lead to efficiency throughout all flight regimes. Fixed pitch propellers are designed as either cruise or climb propellers. Climb propellers are designed to turn high RPMs by a low fixed pitch. Cruise propellers are designed to turn lower RPMs through a high pitch design. Think of this like an oar through the water. When the oar is at a fine pitch, it will slice through the water and not pull a boat forward. If the oar is at a slightly feathered pitch, it can more effectively pull the boat through the water. This is similar to a propeller moving through the air, taking a bigger bite out of the air, thus pulling the airplane faster, causing it to cruise faster. The aero propeller is able to change pitch to be efficient through both climb and cruise flight regimes. The way this mechanism works is through the use of increased oil pressure being sent to the hub of the propeller, actuating a piston which changes the pitch. During the takeoff roll, the propeller control is in the full forward position and thus outside of the governing range of the propeller. This will cause the propeller to act like a fixed pitch propeller. After reaching 500 feet AGL, the Piper Aero Standardization Manual calls for the use of 25 inches of manifold pressure and the pilot to limit the propeller back to 2,500 RPM.
Alright, this is a maintenance diagram of the Piper Aero propeller. One of the main points of the use of this diagram is to show that there actually is a spring located in this propeller. Unlike what a lot of people believe, the spring is actually used to bring the airplane's propeller back towards a low-pitch, high RPM setting. Unlike the spring that's in the Seminole propeller, which actually is a feathering force used in that propeller to bring the airplane's propeller towards a high-pitch, low RPM setting. The next component we're looking at is the propeller governor. Notice the propeller governor is located on the accessory case of the IO360 C1C6. I can't stress enough that it's not located in the dome of the propeller. Notice as the propeller is actuated, we'll see the propeller being moved, the device being moved on the upper portion of our governor. This is actuating the speeder spring and pulling the flyweights either inward or outward to bring the propeller towards an on-speed condition. The governor has a pump which accelerates oil pressure to 275 psi. Notice this oil line will feed up towards the front of the engine and into the propeller dome to actuate the piston, which changes the pitch of the propeller. Here we have a diagram of the Piper Aero propeller governor. It's located on the accessory case on the rear of the IO360 C1C6. Similar to the engine-driven fuel pump, this governor is driven as the camshaft turns in this engine. The rotary motion will be translated through to a rotary motion on a pump. This pump will boost the engine oil pressure, which is typically 90 to 100 psi, up to 275 pounds per square inch.
This increased oil pressure is necessary to cause the propeller to fight the aerodynamic forces acting upon it. During flight, there are four forces which act upon a propeller. The first force is the thrust bending force. As the throttle is brought forward, the propeller begins to rotate faster. The propeller, in essence, is a rotating wing which creates lift on the face of the propeller. The lift acts in a forward direction, thus bending the propeller blades forward. This force tends to move the propeller towards a lower pitch. The aerodynamic twisting force causes the propeller to rotate about its center of lift, thus rotating it towards a low-pitch, high RPM setting. Centrifugal force also acts upon the propeller, moving it towards a low-pitch, high RPM setting as well. The final force acting on a propeller is torque bending force. Torque bending force is due to the Newtonian law stating that for every action there is an equal and opposite reaction. As the propeller turns, it is forced in the opposite direction.
So, as we start our engine, oil will begin to flow through the governor pump up to the base of the pilot valve. Now typically as we take off, we get to 500 feet in our aero and pull back 25 squared. So as you take your hand on the propeller control and pull back, what you're actually doing is pulling the speeder spring outwards, which is attached to this pilot valve, which causes your flyweights to fly outwards. Now what happens is the pilot valve moves forward, oil pressure will be allowed to flow up to the hub of the propeller. This oil pressure up in the hub of the propeller causes the propeller to move towards a high-pitched, low RPM setting. Now, as oil is directed upwards, we'll move back towards an on-speed condition. The on-speed condition causes the flyweights to move back inwards towards their neutral position, the speeder spring back towards a neutral position, and the pilot valve attached to this entire assembly will center itself, stopping any oil flow to or from the hub of the propeller. So let's say now as we get airborne, we move our aircraft violently nose upward and we go towards a prop underspeed condition. The propeller system of the Arrow will maintain on speed 2,500 RPM. The way that it does this is through the use of the flyweights. Notice, as we pitch back, the flyweights move inwards. The pilot valve assemblies attached to the speeder spring will move downwards as the speeder spring is stretched. Oil is allowed to flow from the hub of the propeller up and back into the oil sump of the engine. So oil is drained from the hub, bringing it back towards the low pitch, high RPM setting. On-speed condition occurs as the flyweights move back outwards, the speeder spring will be compressed once again, and our pilot valve will move towards a neutral position and no oil will be flowing through the system, bringing the airplane back to the predetermined RPM is set.